In this example, we are going to look at two cyclists. One is cycling at a velocity of 15 meters per second and then passes a junction. Then he decelerates at a constant rate of 0.6 meters per second squared until he comes to a rest. A second cyclist travels at a constant velocity of 4 meters per second and passes the junction 4 seconds after the first cyclist. In other words, at the time that the first cyclist passes the junction, the second cyclist is behind the first cyclist. Okay? Find the time at which the second cyclist passes the first and the displacement from the junction when this happens. Now, we don't know if this is going to happen before the first cyclist comes to rest, right? Or while the first cyclist is still decelerating. So the best thing to do is to draw ourselves a little picture of what's going on just to help us work out what's happening. Okay? Now, the second cyclist is behind the first cyclist, so we need to set ourselves a position, right? And we're going to call the junction is going to be our starting position, right? We're going to call the direction away from the junction, right, in the direction that they're cycling as the positive, and we're going to call anything behind the junction negative, okay? So the first cyclist is cycling along, passes the junction and starts decelerating, and eventually is going to come to rest somewhere over here, and is going to travel some distance here, and we can call that displacement 1, okay? The second cyclist is 4 seconds behind the first cyclist at the time that the first cyclist passes the junction. And so the second cyclist will most likely be here somewhere, okay? And they will travel past the junction, and eventually at some point they will pass each other. And this we can call displacement 2. This is the displacement of the second cyclist. Now, the very important thing when we talk about displacement is, even though the second cyclist will have covered a greater distance, right? Displacement does not take in distance into account. It doesn't care for how far something has traveled, okay? What displacement is a position away from a starting position, okay? We've specified our starting position as the junction, and we can work out that if we want these two cyclists to pass each other, that means that their displacements at any given time must be exactly the same, right? It doesn't matter where or when, right? Or it doesn't matter that the second cyclist will have covered a greater distance, right? What we're interested in is the displacement, the distance away from the starting position to some point, okay? And in order for them to be at the same position, right, because that's what displacement is, position, their displacements must be the same. So what we need to do is we need to create two functions with respect to displacement and time for these two cyclists separately, and then we will look at them together, okay? We'll combine them at the end. So let's have a look first at cyclist number 1. Right? Let's list the information that we want and the information that we're given. Okay, we are given the fact that the cyclist is traveling at a velocity, an initial velocity of 15 meters per second. And I'm going to call everything that has to do with the first cyclist, I'm going to notate it as number 1. We know the acceleration for the first cyclist is negative 0.6 meters per second because it's deceleration. And we also know that the final velocity, while not important, we will just list it, is going to be 0 because this cyclist is going to come to a rest. Now, we would like a function in terms of displacement and time, right? We don't actually care for the displacement or the time because we don't know at what time or at what displacement they're going to pass each other yet. So it doesn't help that we work out where the cyclist will be when he or she comes to a rest, right? We care about creating a function that could give us any displacement with respect to time. And if you can sort of wrap your head around this, we have constant deceleration, which means that we're going to have some kind of quadratic function for the displacement time. Okay? So the formula we would like to use is going to be displacement is equal to initial plus time, because we want time to be a variable, plus a half a t squared, right? I haven't bothered using the one for velocity, final velocity, because again, as I said, we don't really care what the final velocity or where the final velocity is. So let's plug in our variables, right? Displacement for our cyclist is S1. Initial velocity is 15 meters per second. With respect to time, 1, all right? Whatever time 1 happens to be. Plus a half acceleration of minus 0.6. And we're going to have time squared, but this is time 1 squared. Okay, so very important. Everything here has to do with cyclist number 1. We will have to find a way to relate cyclist 1 and 2 at some point, but for now we're going to treat them separately. Okay. So just tidying up here, we can say the displacement for cyclist number 1 is equal to 15 t1 minus 0.3 t squared. That's the displacement function for cyclist number 1. Let's look at cyclist number 2 now. Okay, let's go and look at the information we're given for cyclist number 2. Cyclist number 2 is traveling at a constant velocity, all right? So we just have velocity of 20 meters per second. Okay. Again, we don't know the distance or the time where these two will pass, so we would like some kind of function that could give us any time or with respect to this person's velocity. Now this is constant velocity, right? So we would like an equation for displacement for second cyclist with whatever time second cyclist is traveling at. The function we're going to use for constant velocity is displacement equal to velocity times time. And placing in our variables for the second cyclist, cyclist 2, his displacement must be equal to his velocity, which is 20 meters per second, times the time that he's been cycling. That would give me the position for him with respect to time. Now, one important thing that we need to remember, okay, is that this cyclist did not start at the starting position. This cyclist was 4 seconds behind the first cyclist. So what we can say is that the time for the second cyclist, right, in terms of the first cyclist, right, if we had to look at the first cyclist, he is 4 seconds behind, okay? He's not at 0, he's at minus 4 seconds, right? This means that we can quickly change our displacement equation for our second function with our new time, right? So the displacement for the second cyclist is equal to 20 time 1 minus 4. So if we compare the two functions now, you'll notice that we have similar time. This should not be down over there. Sorry, this should be t1 squared. Okay, we are using the same variable for time, right, in both of our equations. Okay, we've related the time for the second cyclist in terms of the time for the first cyclist, right? Because I said we have to compare these two at some point. Now, the initial question asks us find where the displacement and at what time these cyclists pass each other. And they will pass each other when their displacements are the same. So in other words, if I want to find the point where they pass, that is the point where displacement for the first cyclist is equal to the displacement of the second cyclist. And so because I've made my time relatable to both, right? If I had not changed my time for cyclist number 2 to be in relation to cyclist number 1, I would be comparing two different equations where their variables were not the same. Okay? So to give you an idea, what you would end up doing is this, which is incorrect. You would be saying 15 time 1 minus 0.3 time 1 squared is equal to, we'll go back to the incorrect one, right, which would be, is equal to 20 time 2, okay? These two are not the same. They may as well just be different variables, okay, because they are not the same. What we had to do was we had to relate them somehow. And we related them by saying, well, time 2 is just equal to time 1 minus 4 seconds, right? So now we could compare them. So comparing them correctly, we're going to say 15t. We can just drop the time now because we know that the times are the same. Minus 0.3 t squared is equal to 20t. Okay, and here we just have a simple quadratic that we need to solve. And my apologies, I've done exactly what I said to you. That's wrong. This should be 20t minus 4. Right, let's just solve this quadratic. This is 15t minus 0.3t squared equal to 20t minus 80. We can multiply everything by 3. That will, everything by 10. That will cause the 0.3t squared to become not a decimal. So we can get 3t squared, and I'm going to change all the signs. I'm going to move this to the other side. 3t squared minus 15t. Sorry, this will not be 15t. This will be 150t. On the other side, we'll have plus 200t minus 800. Adding those two together, we're going to get plus 50t minus 800 equal to 0. And now we just need to factorize. If you don't want to factorize, you can just complete the square or use the formula. But we can work out this is going to be t, this is going to be 10, and this is going to be 80. So minus 80 or plus 80 minus 30 gives me 50, and 80 times minus 10 gives me 800. So those are my factors. That's going to give me a time equal to 10 or a time equal to negative 80 over 3. So I'm not interested in the negative time, right? What this is saying is that at some point before they've met, now they have met before. So before the junction, because the cyclist in the first scenario was ahead, right? they will have met some time before. But we can ignore that. We want to know the time where they met after the junction. So this happens at t equal to 10 seconds. So 10 seconds after they pass the junction, they meet up. Okay. Now we need to find the displacement, and we can use either one of our two equations to find displacement, right? Based on time, right? And very importantly, this is time 1, okay, not time 2. So we cannot just put this into the displacement is equal to 20 t2, because t2, we haven't solved in terms of t2, time 2. We've solved in terms of time 1. So with that in mind, I'm going to use that displacement is equal to 20 time 1 minus 4, which is equal to 20. Time 1 was 10 minus 4. That gives me 20 times 6, which is 120 meters. So they pass each other 10 seconds after the junction, 120 meters away from it.